When we look at a blueprint, we trust the geometry. We see absolute numbers in ink and assume the parts will obey them. But every dimension you put on a drawing is actually a highly specific claim about temperature, and almost nobody bothers to write the temperature down. The physical world refuses to sit still. Even the scientists at NIST, maintaining the international standard for the SI meter, have to constantly correct for the refractive index of air and the thermal expansion of their own reference materials. The physical meter itself has to be told what temperature it is. Look at two 1-meter structural metals, aluminum and stainless steel. Cool them to the cryogenic scale and they do not shrink together. Aluminum shortens by 4 millimeters, stainless by 3. At that extreme, they disagree by a full millimeter. Because these bonded materials hold very different opinions about their physical size, a perfect fit at room temperature is an illusion. It is a temporary truce, but shatters the moment the weather changes. Engineers attempt to manage this chaos by relying on strict testing standards to predict exactly how materials will behave in the wild. This chart maps the temperature boundaries of those standards. Notice the standard known as D696, written specifically for plastics. It runs down to -30 Celsius, but then stops cold at 30 degrees Celsius. A dark polymer car panel parked in July will easily exceed the maximum temperature of its own standard test method. And that panel is usually clipped directly to a metal bracket, characterized over a range 10 times wider. When we design strictly within these idealized test ranges, we assemble parts that are physically bound together, yet operating under entirely different rules. Expansion you refuse to accommodate does not simply disappear. When a material tries to grow but is forcefully restrained by its environment, that blocked movement converts directly into force. A structural buckle isn't a failure of the material's inherent strength. It is a massive compressive load that finally ran out of places to go. The railway industry learned this the hard way. Federal law now mandates exactly how track engineers manage this force. Before laying continuous welded rail, they must file a specific geographic neutral temperature, the precise temperature where the steel is completely at peace. This logic tree shows a calculated bias. Setting the neutral temperature high guards against summer buckling, but invites the rails to pull apart in extreme cold. Setting it low completely inverts the risk. You don't need continent-spanning tracks to see this physical law in action. The exact same mechanism destroys sensitive aerospace electronics. NASA maintains an entire packaging program, partly to deal with thermal cycling fatigue in tiny joints of eutectic tin-lead solder. The microscopic solder fractures because the silicon chips and the fiberglass boards underneath them stubbornly disagree about their size. From heavy industrial rail infrastructure to microscopic orbital circuits, the physics of absolute, refusing to accommodate a material's movement, guarantees structural violence. This forces a harsh reality during the initial concept phase. The true engineering challenge is almost never calculating the precise mathematical size of a gap. You must choose which specific part gets to be the fixed anchor, the datum, and which is permitted to move, the fire. Slotted holes, compliant adhesive beads, mechanical clips, and floating mounts are just the same datum versus slider decision wearing different clothes. Designating that anchor sets the single fixed point for the assembly. That point dictates the direction of the growth, and ultimately decides exactly what the object will look like on the absolute hottest and coldest days of its life cycle. Solving a mechanical constraint immediately introduces a new experiential problem for the person buying the product. A joint left free to slide so it doesn't buckle is also free to vibrate. Every floating mount you design is simply a rattle handed directly to the consumer. And a gap mathematically scaled to survive a -40-degree freeze will look incredibly generous sitting on a showroom floor at 20 degrees. To the user, it reads as sloppy build quality, not engineering competence. When two parts of a system disagree, somebody has to choose who wins. If you refuse to decide in advance, the materials will violently make that choice for you during the first heat wave or hard frost. Design decisions are as cheap as a sketch, but they are brutal once tooled. You have to see every angle and understand every invisible force long before you build.